Hello, welcome to Semiconductor 360 Live, the Israeli edition in the year 2021. I'm Brad Griffin from Cadence Design Systems. I'm a product manager responsible for signal integrity and power integrity tools that work on PCBs and IC packages at Cadence. Today I'm going to talk to you about the challenges of DDR5 in package design, because package design needs to be supplemented with analysis to make sure that your DDR5 interfaces are going to work on your IC packages. So thank you for being here. Let's go over our agenda. The first thing I'll start off with is some information that you may or may not know about DDR, why it's so important, why it's such a signal integrity challenge. And then we're going to get into the challenges specific to you semiconductor vendors out there that need to deal with the package. The package is a very important part of the DDR interface, and we're going to go through why you need to be particularly attentive to your package design and doing exhaustive, detailed analysis to make sure your chips will work within the full system. And the way that we're going to suggest that you can be most successful with that is using an efficient methodology that's been proven by a number of customers and is evolving all the time to be able to support all the various different challenges of DDR5. So let's get into it. When you think of DDR5, it's the next generation of DDR interfaces. That's your memory controller to your memory module. How are you going to deliver the data? How are you going to receive the data from the DDR memory module in a way that meets the JEDEC specifications for bit error rate and for IMASC timing, jitter? There's a number of different things that are going to be a challenge when it comes to implementing a DDR interface successfully within a system. And there's no doubt about it, if you've done DDR any time in your life, DDR2, DDR3, even DDR4, the speeds continue to get faster. DDR5 is a minimum of 48 megabits per second. So that's where DDR4 ended at 3200. So now we're going to go from 48 megabits per second to 6400 megabits per second with DDR5. These speeds are amazingly fast when it comes to a parallel bus. There was a time where we never would have even considered going this fast with the parallel bus. Certainly the serial links, the SerDes channels have been in these speeds and continue to go way beyond these speeds, but dealing with a parallel bus at these speeds is extremely difficult. And to add to the challenge, when you've got multiple bits on a data bus, when you've got multiple bits on a command bus switching simultaneously, you're going to have to deal with making sure that your power delivery system, your power delivery network is delivering a stable power. So with the simultaneous switching noise that can impact that the power and ground associated with that, you're dealing with even lower voltages in DDR5. DDR4 was 1.2 volt voltage swing, and DDR5 is a 1.1 volt voltage swing. So even less margin when it comes to having any sort of impact from simultaneous switching noise. Certainly you need to be able to look at the bit error rate requirements. The JEDEC spec puts that in place. You have to look for read and write. And as I mentioned, the package itself is not the only problem. You don't have to, you're not done when you look at your package model and say, okay, this looks good. You need to make sure that wherever your package is going to sit within the system, that you're going to be able to help your system level customer, whoever is implementing that package in the system, make sure that they can meet those requirements. So you're going to be looking at crosstalk. You're looking at the challenges of being able to break out of a very dense, ball field with respect to the package. And they also need to consider, obviously, from a signal integrity perspective, all the JEDEC requirements and all the various different mask requirements they have when you look at at simulating multiple bits, or if you're in the lab in a prototype with you're using a scope, you're capturing, a long data run. You need to make sure that mask opening is meeting those requirements. And certainly we want to be able to make sure from a simulation perspective, we're able to capture that way ahead of time, make sure that we know what's going to happen when we go to the lab. So there's a lot of things to consider when it comes to DDR5. Now the package, it's a good news, bad news. The package is a small piece of the DDR interface. So if a DDR interface doesn't work, could be a lot of different things that could cause the DDR interface to work. It may not be the package, but here's the bad news. With a package, you can't, all you can do is screw up. You really can't be in a situation where you can say, the pack, someone can make the package design better. You have to make your package design great out of the gate so that you don't screw up. You cannot be the problem as the package designer when it comes to the full DDR interface, which includes, as you can see in this diagram, starting at the transmitter, at the memory at the memory controller, which is potentially going to have a decision feedback equalization module associated with, so you can look at being able to capture the equalization that takes place of that. You're going all the way through to the redistribution layer. That's also part of what you're looking at the chip level, the semiconductor, and then there's the all important package design. So you really need to make sure that when you extract and model that package, push it into the PCB, going potentially through a connector all the way through to a DIMM module. You need to be able to make sure that all those pieces plug and play together that work within the system. So here's one of the things we really have to consider about with the DDR interfaces going at speeds at a minimum of 48 megabits per second. We've got a history of doing modeling and extraction of DDR interfaces using, let's say, non-full wave 3D field solvers. Got a history of using, say, a hybrid solver to be able to extract that DDR interface and create an S parameter that would then plug into the system. And I wouldn't take away that methodology for early on in the design cycle, but there's going to come a point at these kind of speeds where you're going to need a little bit more reliability, a little bit more confidence, if you will. You're going to be able to need to extract that using a full wave 3D field solver. And let's be honest, you've got 64 bits of data, you've got 64 bits of address bus, you've got command, you've got strobe, you've got many signals that you're going to have to extract. This is way beyond what many people consider being a reasonable thing to be able to consider for a full wave 3D field solver. But we need to take a look at what we can do as a methodology to be able to support that these days. And so ultimately, we want to make sure that we provide a package that can plug into a system like we see here that will meet the full JEDEC specifications, because without that, you're not going to sell your semiconductor in volume. And that's obviously what everybody's looking here, get their semiconductor out in volume situations where you can be successful and reap all the profits from all that investment that you've made to get on that particular design. So you need a methodology. A methodology that's going to be successful should always start with proven technology. And let me say that when it comes to design tools on the marketplace, there's really a clear market leader. A clear market leader when it comes to design tools. If you look at all the manufacturing companies out there that are doing package design for their customers, they're all relying on one design tool. You look at what it takes. If you're one of the top semiconductor companies out there, it's very consistent across which package design tools companies are using. So that design tool is one that you want to consider. It's very flexible, supports many different types of packages. As you can see here on the upper right, whether it's a flip chip, whether it's a wire bond, whether you need to stack die, whatever that consideration is, you want to look at where is the market leader in package design tools. And once you've selected a design tool, you need to consider, what am I going to use to perform analysis of that package? And let's be honest, we know a lot of people today go off and use whatever point tool they want. But is that really efficient? especially when I want to propose to you that part of your design process could be using an InDesign analysis technique that as you're designing the package, you could actually be side by side looking at how is this how is this design working? Do I have too much crosstalk? Do I have too much coupling? Do I have any impedance discontinuities? Have I balanced all the inductance and the resistance across my pins equally in this package? To be able to look at that early on as you're designing the package, that can really be a lifesaver, because certainly you don't want to find these problems late in the design cycle. These are the easy things to fix. So starting out with an analysis technology where the technology is sort of built right into an InDesign analysis flow, this is really a key way to be able to provide a methodology that's going to get your product out on time. All right, so let's continue on. As once you've created this design, you may be getting close to your final interface when it comes to DDR. There, as we've already mentioned, there's a lot of signals that need to be analyzed in tandem together. You don't want to limit to just look at what you think is going to be the worst case signal. And we've dealt with a lot of customers that we know that that is a methodology that they use. Maybe they try the hybrid solver, they get some reasonably good results, but when it comes to the full wave extraction, they just don't have a tool. Many people don't have a tool that will support a large extraction of, let's say, a 64-bit data bus like you have with DDR5. So we have some examples where we've been looking at people that they use, the better part of a work day to look at just one signal coming out of that DDR5 interface, being able to model and extract that. Um, while they use that as an approach to say, well, at least I'm able to see from this, or maybe let's just say maybe it's a couple signals, so you can look at some kind of crosstalk. They think they've maybe had the worst case situation, so they sort of rely on that. They get good results for that. They say, okay, I'm going to cross my fingers. I'm going to go ahead and tape out this package design. But that's no way to live life, right? You don't want to live life with your fingers crossed. You want to live life with confidence. So that confidence can come when you have a tool that can not only do that single net extraction much faster than the 7.75 hours we have in this example, can do it 6 times faster. It basically cuts it down to 1 to 1.5 hours, and you get the exact same results that maybe the legacy tools do. But now you can use that same tool to run a much larger extraction, and then maybe in like closer to half a workday, you're able to extract the full DDR memory interface. This is something that customers really tell us at Cadence that that is a key enabler to them to make sure they have full confidence in taping out their package design for memory controllers. And you could be looking at just a bump to ball memory interface for DDR5, or you could be looking at something like this, where you've got multiple die inside your package, and you've got the controller, and you've got the memory, and now you need to do a full wave 3D extraction that basically tracks the signal all in that multi-die configuration all the way through. So at 6400 megabits per second, again, you just don't have the leeway to say, hey, I'm going to just do one signal. You want to do the full bus. And we have examples where we've seen customers be able to extract, even on a relatively small computer, an 8-core computer, be able to extract that full memory interface out in less than 9 hours. So in less than basically in a work day, they're able to perform that extraction. This is really kind of groundbreaking sea change methodology when it comes to doing DDR modeling and extraction of the full interface using full wave true 3D interface analysis. So we want to encourage you to look at that as part of your proven methodology when it comes to DDR5. And so now you've extracted out the package. Certainly I would hope that internally you've got a reference design where you're going to put that package on a printed circuit board and communicate all the way to the actual memory module. So you want to be able to make sure internally you can look at that full system. So as we mentioned, the decision feedback equalization that occurs within the memory controller, it's also happening within the memory module itself now. So being able to get those models and plug that equalization in so that you can actually have your simulation perform the same way that the interface is going to perform when you get the test case on the bench. You want to see that. You want to see all the interconnect in between extracted with full wave 3D accuracy. And then once you've got all those models plugged together into a hierarchical system, then you're going to look and make sure that you're meeting the JEDEC specifications for the eye masks, that you can run many, many bits. You can look at bit error rate using full wave extraction, and that you can use the simulator to run channel simulation, where you're looking at millions of bits being simulated using the equalization models, the decision feedback equalization models for that channel simulation, to give you the real information. Is this system going to work when it comes to the full system simulation for DDR5? And this is going to be best done if you work with a single vendor to provide the solution, a single vendor for design, a single vendor for extraction, a single vendor for the multi million bit simulation that you'll need to perform the bit error rate requirement simulations. So let's be honest, that whatever kind of chip you're designing, you're probably going to have to interface with memory, because that's just part of what is part of any system today. Today, DDR5 is the emerging standard. DDR4 has been around for a while. It's maxed out at 3200 megabits per second. So we're moving up to 6400 megabits per second with DDR5. This is where the industry is going. Before you know it, the price of DDR5 is going to be lower than DDR4, and it's the direction that's going. So you need to get on board now with dealing with these challenges. And so if you work with a single vendor to provide your design tools, your extraction tools, your simulation tools, you're going to be on your way to simulation, to a sign-off DDR5 interface in your package much more effectively. And we hope that you will contact Cadence Design Systems for more information on this flow. So with that, I thank you for your time, and I hope you enjoy the rest of Semiconductor 360 Live from Israel. Thank you very much.